In this lesson, you will be learning about metal extraction in general, but in particular about iron extraction using blast furnace and the reactions that goes inside blast furnace. To understand this really well, you need to be familiar with these terms and the key words that's on this page. I'm going to give some examples of and explain as much as possible, but don't worry if you don't get all of these words right now, because as you go through the different pages of this lesson, you will possibly enhance your understanding of each of these terms. So read the meaning, and even if you don't understand fully, you go into the lesson and you can always come back to slide number 1 to have another look at these words to make more sense of them. I want to just show you first of all what minerals are. This word here, these are naturally occurring inorganic substances, which means they are not made by humans. They are naturally occurring and they are present on the earth or just under the earth's surface. Sometimes they have to be dug up. These are normally found as mixture of minerals with other substances, particularly in rocks. Inorganic means, as I already said, it's not made by living things, and that's really important to understand. What you see here are examples of minerals. On your left, the pink crystal is called rhodochrosite, but you don't need to know the name and remember this name of this mineral, but all you have to remember is a fact that they have a formula, a definite composition, a chemical composition, and they have a formula like this, and all minerals have definite chemical composition, and that's really important to understand. What you see here on your right is another mineral called malachite, and that is the ore for copper. Copper metal is extracted from this mineral, and it's got a formula Cu2, CO3 and OH twice. Okay, so that is, you don't need to know the formula and remember this for any purpose, but all you need to understand is they have definite chemical composition, and these are very useful things in minerals, because metals in particular and many other useful substances can be extracted from minerals. Next, you should understand what mixtures are, because rocks are essentially mixtures, and many minerals exist as mixtures in rocks with other substances as well. A very simple example for this is like a sugar solution, which you see here, right here. That is sugar solution, where you can see the water molecules here, and that's water molecule in liquid form. You can see this shape. It's a fairly simplified structure of sugar. Over here you can see that orange molecules of sugar. You can't see the full molecule. Sugar in fact looks like this. It's pretty complex, so I'm trying to show you in a very this image shows a very simplified form of sugar. The whole molecule cannot be shown. So this is a mixture where, as you can see clearly, the atoms of water are connected. They are bonded together. The atoms of water, which is 1 oxygen and 2 hydrogen atoms, they are connected, chemically bonded. Whereas if you look at the sugar molecule, there is no connection between the sugar and the water. They can exist anywhere, and that's the nature of mixtures, because they are not chemically joined together, and they can be separated as well. And if you can think of this, if you evaporate the water away completely, you get the sugar left behind, and if you want water, you can condense that, and that's what mixtures are. They are two different substances with two separate chemical formula. So just to reinforce that idea, Mixtures are things that have more than one substance that are not chemically joined by chemical bonds. So mixtures, this is what we've just looked at with two examples. Okay, next is ore. Now ore is an example of a mixture, as it is generally we refer to rocks which contain a good amount of a particular metal or an element that can be profitably extracted. So this means it contains a compound of a particular element of interest that you're interested in. For example, copper. The ore for copper, as we've just seen under mixtures, it's malachite that contains a copper compound, copper carbonate. Now sometimes ores can contain pure elements, not in the form of compounds. For instance, gold. The gold ore it contains gold in its purest form, like it's not in the form of a compound. As it is, it exists. So basically, you have a rock generally, or soil, or any other source that contains a good amount of a particular metal element in the form of its compound that can be profitably extracted. This means the money that you spend in extracting is worthwhile, and you will still be able to make a profit by selling the metal that you get from it. Next, we are going to be looking at blast furnace. This is a tall tower structure in which iron is extracted. So the whole reaction between the iron ore and the carbon and the limestone happens inside the blast furnace and at very high temperatures. It is built with special bricks to withstand the high temperatures, and this is something that we are going to be looking in more detail in this lesson. So if you cannot understand or picture this in your mind, you can leave this until later when you get into the lesson. Limestone, as you probably are aware of this, it's a type of rock, soft rock, sedimentary rock. It mainly contains the chemical calcium carbonate. Later on in this lesson, we'll be looking at the chemical formula of calcium carbonate. You probably already know this. Reduction reaction. This is a particular reaction which you come across very often when you learn metal extraction or extraction of metals. In this lesson, we'll be particularly focusing on iron extraction. That is also mainly a reduction reaction. In general, reduction reaction is a chemical reaction in which you remove oxygen atoms from a compound that is bonded to oxygen atoms. For example, you have copper oxide, which is a copper compound, and if you remove that oxygen atom by a chemical reaction, that is reduction reaction. You're reducing copper oxide and you get copper from it, and that's a reduction reaction. Click on the next slide to move into the lesson. So let's look at extraction of iron in particular. What you see here is iron ore, which is basically a rock which contains mainly a compound of iron. In this case, it's iron oxide, who's got a formula Fe2O3. This is the main component of the rock here. It also contains impurities, mainly silicon dioxide, which is this SiO2. Another substance we'll be using in the extraction of iron is carbon, and it can be referred to as charcoal, coke, or coal. These are all commercial names or well-known names for carbon, but they all contain this element carbon in them mainly. Another substance, the third one we'll be using in the extraction of iron, is limestone, whose chemical formula is calcium carbonate. So these are the three main substances involved, and we should be familiar with this. And also this is the impurity. Silicon dioxide is essentially sand or quartz, and this is one of the main impurities that's present in the iron ore. Click on the next slide to go into the extraction of iron in the blast furnace. The blast furnace is a giant structure in which the chemical reaction takes place. The chemical reaction between iron ore, which is iron oxide, and coke, which is mainly carbon, and limestone, which is calcium carbonate. And they're all added here. Iron ore has a formula, as you know, mainly Fe2O3. It contains mainly iron oxide. And coke, which is mainly carbon, and limestone is calcium carbonate. It's really important to understand that they're all added here at the top of the tower, and it flows down the tower this way. Okay, and hot air is blown through this opening and this opening, and it travels upward in the blast furnace, and the reaction takes place in this area, and it's extremely hot, and at this temperature the reaction takes place. Let's get an overview of what's happening in the blast furnace, and we can look in the reactions in more detail in the next slide. Okay, now as we already know, iron oxide contains oxygen, where the iron is chemically bonded to oxygen, and that carbon reacts with this iron oxide. Particularly, it takes the oxygen away, so the oxygen is removed by the carbon atom. The purpose of calcium carbonate is to remove the impurity. As we know, it's silicon dioxide, SiO2. This is essentially sand. Let's understand the reaction between iron oxide and carbon. Carbon initially becomes carbon dioxide by reacting with oxygen, and then as there is less oxygen inside the blast furnace here, it reacts again with the incoming carbon to become carbon monoxide, and it's this carbon monoxide reacts with iron oxide, Fe2O3, to remove the oxygen, and we finally end with iron. And iron being heavy, it sinks right to the bottom of the blast furnace. Now, calcium carbonate, as we know, is limestone, and in the intense heat of the blast furnace undergoes thermal decomposition, and it breaks down into calcium oxide and carbon dioxide. Now, it's actually this calcium oxide that reacts with the silicon dioxide to make calcium silicate, which is CaSiO3. So let's summarize that information, all that information, all that reactions that happens in the blast furnace. Initially, the carbon becomes carbon dioxide, and then it becomes carbon monoxide, which reacts with iron oxide to produce iron. Calcium carbonate, which is the limestone, breaks down into calcium oxide and carbon dioxide. The calcium oxide reacts with silicon dioxide, which is essentially sand, to produce calcium silicate. Now, we're going to be summarizing all these reactions in the next slide. It's also useful to understand that iron, which collects at the bottom of the blast furnace, can be poured through that opening there, as it's a liquid, and so is the slag, which is calcium silicate, can be poured through that opening and can be removed from the blast furnace. Click on the next slide to go and have a look at the details of the chemical reactions that take place in the blast furnace. initially carbon reacts with oxygen to produce carbon dioxide. This reaction is already balanced, as there is one carbon here, two oxygen here, one carbon there, two oxygen there. And then this carbon dioxide reacts with more incoming carbon to produce carbon monoxide. So let's have a look at that. So carbon dioxide plus carbon giving carbon monoxide. Okay, and that's a toxic gas, carbon monoxide, and that's the one which reacts with the iron oxide to produce iron. Let's have a look at that. So carbon monoxide plus iron oxide to produce iron and carbon dioxide. Now notice that I have left some space here as to balance it. Later on, the space before every compound that we have here, every substance that we have here, including iron, is for balancing this equation later on. So these three reactions explains how you get iron from iron oxide. So we get iron here from iron oxide, and the next two reactions is about the calcium carbonate removing the impurities. Let's have a look at that. So initially calcium carbonate breaks down into two and it forms calcium oxide plus carbon dioxide, and then this calcium oxide is going to react with silicon dioxide. So calcium oxide plus silicon dioxide giving calcium silicate. And we know this is the molten slag that we saw earlier in the previous slide, and that is the molten iron that we saw earlier, molten iron in the previous slide in the blast furnace, and that's how it is formed. Okay, now it's a question of balancing this equation. Okay, now as you notice, you might notice that these two equations, this one and that one, is already balanced. Calcium, one calcium here, one carbon there, 3 oxygen here, 1 plus 2, 3 oxygen on the right hand side. Have a look here. On the second equation is 1 plus 2, 3 oxygen on the left hand side, and it have 3 oxygen on the right hand side, one calcium here, one silicon and one silicon there. So that these two equations are balanced, and so are these two. You can check this. But this equation is not balanced, another third equation. Okay, to balance that, you would need to put here a 3. Now it's advisable not to put a 2 here, because that will make the total number of oxygen into an odd number. So I'm trying to put a 3 here, because that 3 oxygen plus this 3 oxygen makes it 6 oxygen atoms on the left hand side. So it will be easier to convert this into 6. Now, so by just putting a 2 here, or 3 here rather, and that becomes a 6. So the oxygen is balanced now. All you have to balance is the iron atom. So I can do that by putting a 2 here. So iron is balanced now. Carbon, there is 3 carbon here, 3 carbon, so that's balanced. 3 oxygen plus 3 oxygen, 6 oxygen atoms on the left, and you have 3 times 2, 6 oxygens on the right hand side. We are going to be looking at this equation in detail on the next slide. The whole process of balancing equation, the trial and error method of balancing an equation. We have to look at that in detail. I simply said it's a 3 that goes here to make this oxygen atom an even number, is one way to look at it. But you might want to look at the next slide to understand how the whole process works, how you would do it. To complete all the equations and balance them. I said earlier these two equations are balanced, but in fact I just noticed that this one is not, this equation is not balanced. So I'm going to do that right now by actually putting a 2 here. That's all I had to do. And now when I put that 2, what happens is you have now 2 carbon atoms here, and you have 1 plus 1, 2 carbon atoms on the left hand side, 2 oxygen atoms here, 2 oxygen atoms on the right hand side. So that's also balanced now. So the only equation that we're going to be looking in detail is that one. So please go to the next slide to have a closer look at that equation. So let's look at that tricky equation that we saw in the last slide once again, to take you through the process of how you would approach it. Try something and get it wrong, and finally getting it right. So I'm going to take you through that process. So we have carbon monoxide plus iron oxide, Fe2O3, giving, notice that I have left space before each substance there, and you get iron plus carbon dioxide. Okay, so if you were to do it, you would start off by looking at this carbon atom. I'm just trying to see how one would approach balancing this, and just go and make errors and correcting the errors and balance it finally. Okay, so we have 1 carbon here, 1 carbon seems to be okay, same number on both sides. And if you look at oxygen here, 1 plus 3 gives you 4 oxygen, but you got only 2 here. So you'd be tempted to put a 2 here. Which is that. Okay, now that makes this carbon atom into 2. Okay, so but the oxygen seemed to be okay, as you got 4 oxygen here, 2 times 2, that's 4 oxygen, but the carbon number has changed. Now if you put a 2 here again, then what happens is the carbon seemed to be okay, but the oxygen now has become a problem now. 2 oxygen here plus 3, that's 5 oxygen, and you have 2 times 2, 4 oxygen. Now we'll be going in cycles. If you do change this into 2.5, then you'll have the wrong number of carbon atom here. So if I put 2.5 times 2 becomes 5 oxygen. Oxygen will be balanced, but now you won't have the carbon number the same. So we have a problem here. We end up going in cycles. To balance the iron, however, is straightforward. You put a 2 here. That seemed to be okay. So but this 2 that you put here doesn't seem to work. So instead of a 2, now we're going to try a 3 here. And there is a logic to this, because then you have an even number of oxygen atom. 3 oxygen atom plus that 3 becomes 6 oxygen atom here on the left hand side. It's better to have an even number than the odd number that we had here. 2 plus 3, 5 oxygen atom. And that is one way to approach this. So you got 6 oxygen atom on the left hand side here. So to make this into 6, I have to put a 3 here. So 3 times 2, 3 times 2 oxygen becomes a 6. Now as we've done earlier, to balance this 2 iron atoms, I need to put a 2 here in front of that iron atom there. So now check once again, do we have the same number of carbon atoms here? Yes, we have 3 carbon atoms. We have 3 carbon atoms, 3 oxygen atoms plus 3, we have 6 on the left hand side, and 3 times that 2, that becomes 6 oxygen atom on the right hand side. So now we have a balanced equation. Now that we have seen how to balance this equation, we have to look at this most important equation of the blast furnace reactions in a bit more detail. This part of the lesson is only for higher students, and this is often asked in at grade A level of questions. So what you need to understand for this part is what is reduction and how that works. And we're going to be looking at just that. If you look at this compound here, iron oxide, it is a compound where iron is chemically bonded with oxygen, and carbon monoxide is another compound. Now, as you go from here to here, you can see that oxygen has been removed by the carbon monoxide, and that carbon monoxide has become carbon dioxide. In effect, the iron oxide has lost the oxygen, but the carbon has gained the oxygen to become carbon dioxide. So the carbon initially had only one oxygen. Now, going from here to here, the carbon now has two oxygens. So the carbon has gained the oxygen, iron has lost. So we say the iron oxide has been reduced to iron. And that reaction is called reduction reaction. When you remove oxygen atoms from a compound, that is a reduction reaction. Another possible question in this area, based on this reaction, is that how carbon is able to remove the oxygen from iron, but not from aluminum oxide, which is a very similar compound, aluminum oxide, and carbon is not able to remove that oxygen from aluminum oxide. And the explanation is this: based on, it's based on the reactivity series. We know carbon is more reactive than iron, and so it is able to remove that oxygen, but it is less reactive than aluminum. In other words, aluminum is far more reactive than carbon, so it is strongly attached to oxygen. Carbon is unable to remove that oxygen.